Look up at the night sky on a clear evening, and what do you see? A scattering of distant stars, maybe the moon, a vast and seemingly silent expanse. It's a view that feels familiar, almost comforting in its constancy. But what if I told you that everything you think you know about that starry canvas, everything you learned in school about our solar system and the universe beyond, is merely the cover of a book whose most incredible chapters have been kept hidden from you? We're about to pull back that cosmic curtain. Welcome to a journey through 30 space facts you didn't learn in school, a collection of cosmic secrets so bizarre and mind-bending, they'll completely reshape your understanding of reality. Forget the dry diagrams of planetary orbits and the simple lists of gas giants. The universe is far stranger, far more mysterious, and infinitely more wonderful than any textbook could ever capture. It's a place where the laws of physics seem to bend, where everyday logic fails, and where the truth is often more incredible than the wildest science fiction. Think about the sheer scale for a moment. We live on a tiny, fragile world orbiting an average star, one of hundreds of billions in our galaxy, which itself is just one of perhaps 2 trillion galaxies in the observable universe. That's a number so large it's almost impossible to truly comprehend, and within that unimaginable vastness, there are phenomena occurring that defy belief: worlds made of diamond, rains of molten glass, black holes that sing, and voids so enormous they challenge our very definition of existence. This video is your ticket to exploring those hidden corners of the cosmos. We're going to uncover the whispers of the universe, the strange and beautiful truths that your education left out. This isn't just a list of trivia, it's an invitation to reignite that sense of awe and wonder you felt as a child looking up at the stars for the very first time. So get comfortable, open your mind, and prepare to have everything you thought you knew about space turned completely upside down. The adventure starts now. Let's begin with a fact that hits remarkably close to home, quite literally changing the sky above us. Our own moon, that constant, comforting presence in our night sky, is in the process of a slow but steady cosmic departure. Every single year, the moon drifts approximately 3.8 centimeters farther away from Earth. That's about the same rate your fingernails grow in a month. While that might sound insignificant on a human timescale, over the vast stretches of cosmic time, this tiny annual shift completely reshapes the Earth-Moon system. The engine behind this lunar escape is the intricate gravitational dance between our planet and its satellite, a phenomenon driven by tides. You see, the moon's gravity doesn't just pull on the solid Earth, it also pulls on our planet's vast oceans, creating the bulges of water we experience as high tides. But because the Earth rotates so much faster than the moon orbits us, our planet's spin actually drags this tidal bulge slightly ahead of the direct line to the moon. This massive bulge of water, in turn, exerts its own gravitational pull on the moon. This constant, gentle tug does 2 things. It very gradually transfers rotational energy from the Earth to the moon, and that transferred energy pushes the moon into a slightly higher, and therefore more distant, orbit. It's a perfect, if slow motion, exchange of momentum. The consequences of this celestial retreat are profound for the distant future. As the moon steals Earth's rotational energy, our planet's spin is imperceptibly slowing down, meaning our days are getting longer. Billions of years from now, a day on Earth will be significantly longer than 24 hours, and perhaps the most poetic loss will be one of nature's most spectacular sights, the perfect total solar eclipse. The moon's apparent size in our sky is a precise balance of its actual size and its distance from us. As the moon continues to recede, its disk will appear progressively smaller. Eventually, there will come a time, hundreds of millions of years from now, when it will no longer be large enough to completely cover the sun. The era of the breathtaking totality, with the sun's brilliant corona shimmering around a black lunar disk, will come to a permanent end. So the next time you gaze up at a full moon, consider this: you are looking at a companion that is, in the most literal sense, slipping away from us 1 centimeter at a time, forever altering the fundamental rhythms of our world. But while our own moon is slowly distancing itself, the universe at large is actually brimming with some surprisingly familiar, if utterly bizarre, ingredients. If you thought the idea of a drifting moon was strange, wait until you hear about the intergalactic bar. Near the center of our Milky Way galaxy, some 26,000 light-years from Earth, floats a colossal cosmic cloud known as Sagittarius B2. This isn't just any cloud of gas and dust, it's a sprawling stellar nursery, one of the largest molecular clouds in our galaxy, and within its vast expanse, which stretches over 150 light-years across, astronomers have made a head-spinning discovery: it contains vast quantities of vinyl alcohol. To be perfectly clear, this isn't the kind of alcohol you'd find in a cocktail. It's a complex organic molecule, and the cloud holds an almost unimaginable amount of it, enough to fill billions upon billions of Olympic-sized swimming pools. Picture this colossal, swirling maelstrom of cosmic dust and gas, glowing with the energy of newborn stars and laced with this fundamental organic compound. Finding such a molecule in space is a monumental discovery, far more significant than just a fun cosmic trivia point. Vinyl alcohol is what scientists call a prebiotic molecule, one of the essential stepping stones needed for the chemistry of life to begin. Its presence in a cloud like Sagittarius B2 provides a powerful and compelling piece of evidence that the fundamental building blocks of life are not unique to Earth. They are, in fact, being forged in the nuclear furnaces of ancient stars and scattered far and wide across the galaxy, seeded into the vast molecular clouds where new solar systems are born. Every time you look at the night sky, particularly toward the dense star fields in the constellation Sagittarius, you are gazing in the direction of a reservoir of life's potential ingredients. This intoxicating cloud tells us that the universe appears to be hardwired for chemistry, predisposed to creating the complex molecules that can one day, under the right conditions, assemble into something we would recognize as alive. It profoundly shifts the question of life in the universe from, is there anything out there, to a much more likely, where is it all? The cosmos isn't just a cold, empty void, it's a vast chemical laboratory, tirelessly experimenting and laying the groundwork for life on worlds we have yet to even discover. Now, if you thought a drifting moon and an alcoholic cloud were bizarre, prepare to have your entire sense of time turned inside out, because on our nearest planetary neighbor, a single day lasts longer than an entire trip around the sun. Welcome to the topsy-turvy timeline of Venus. This planet, often called Earth's twin due to its similar size and mass, is in fact a cosmic oddball with a rhythm all its own. It takes Venus 225 Earth days to complete one full orbit around the Sun. That is its year. But astonishingly, it takes this world 243 Earth days to spin just once on its own axis. That is its day. Let that sink in for a moment. If you were standing on the scorching surface of Venus, the time from one sunrise to the next would be longer than the duration of the planet's annual journey around our star. To make this celestial slow dance even stranger, Venus rotates in the opposite direction to almost every other planet in our solar system, a motion known as retrograde rotation. On Venus, the sun would rise in the west and set in the east, completing its painfully slow arc across the sky over a period of months. So, what colossal event could have sent this world spinning backwards and so incredibly slowly? The leading theory points to a chaotic and violent past. many planetary scientists believe that in the solar system's formative years, a protoplanet, a massive object perhaps the size of Mars, slammed directly into a young Venus. The titanic force of such an impact would have been almost beyond comprehension, delivering a blow so profound that it could have effectively stopped the planet's original spin and sent it whirling in the opposite direction, leaving it with this extremely lethargic rotation we observe today. Another compelling idea suggests that the thick, soupy atmosphere of Venus, a crushing blanket of carbon dioxide with clouds of sulfuric acid, creates immense atmospheric tides. The gravitational tug-of-war between the Sun and this incredibly dense atmosphere may have, over billions of years, acted as a perpetual brake, steadily slowing the planet's spin to its current crawl. This means the very air of Venus, or what passes for it, contributes to its bizarre temporal reality. The combination of its retrograde motion and its incredibly long day creates a truly unique celestial calendar. From one sunrise to the next, the planet will have completed most of its orbit, meaning a Venusian year contains less than 2 full Venusian days. It's a world where the basic cycles that govern our lives, the rising and setting of the sun, the turning of the seasons, are completely unmoored from our earthly experience, a profound reminder that the universe operates on its own terms, crafting rules and rhythms that can seem utterly alien to us. And from the strange, slow spin of Venus, we journey to the aftermath of one of the universe's most violent events, where the very fabric of matter is compressed into something almost beyond imagination. If you took the entire colossal mass of our sun and crushed it down, you would need to squeeze it into a sphere just over 10 miles across to match the density of a neutron star. These are the cosmic zombies left behind when a massive star dies in a cataclysmic supernova explosion. After the star's outer layers are blasted into space, what remains is an inert core, and if that core is between about 1 and 3 times the mass of our sun, gravity wins an ultimate victory. The force is so unimaginably strong that it overwhelms every other force in nature, crushing atoms themselves. Electrons are literally forced into protons, transforming them into neutrons, and the entire core collapses into a city-sized ball composed almost entirely of neutrons packed together shoulder to shoulder. This creates an object of such staggering density that it defies all earthly analogy. To put it in perspective, a single sugar cube-sized amount of this neutron star material would not weigh a few pounds or even a few tons. It would weigh over 1 billion tons here on Earth. That's the equivalent of taking Mount Everest, the planet's most massive mountain, and somehow compressing all of its rock and ice into a single teaspoon. The physics inside such an object becomes bizarre and otherworldly. As you move from the outer crust towards the core, the pressure increases to such an extreme degree that the neutrons are forced into ever stranger configurations. Physicists believe that deep within a neutron star, the material might form structures they whimsically call nuclear pasta. This isn't a culinary experiment, but a series of phases where the nuclear material, under unimaginable strain, arranges itself into shapes reminiscent of familiar foods. There might be a layer where it forms long, tube-like structures, which they call spaghetti. As the pressure increases further, these tubes might get squeezed into flat sheets, dubbed lasagna. And under even more extreme conditions, these sheets could be compressed into uniform, dense blobs known as nacai. This is matter pushed to its absolute limit, a state that cannot be recreated in any laboratory on Earth. The existence of such phases shows us that under sufficient force, the universe finds strange and beautiful new ways to organize itself. A neutron star is a perfect laboratory of extreme physics, a place where the rules of quantum mechanics and general relativity collide, offering us a glimpse into the behavior of matter under conditions we can scarcely comprehend. It is a monument to the raw, transformative power of gravity, proving that the universe can take something as grand as a star and forge it into an object of even greater and far more mysterious wonder. Just when you thought the universe was a realm of profound and eternal silence, prepare to have that assumption completely shattered. We've all heard the cliché, in the vacuum of space, no one can hear you scream. And it's technically true, the familiar sound waves that travel through the air on Earth have no medium to vibrate in the near emptiness between stars and planets. But to call space silent is like calling a rainbow colorless just because your eyes are closed. The cosmos is, in fact, a roaring, churning symphony of invisible energies, and we now have the technology to listen in. The key lies in moving beyond the narrow definition of sound that our ears are built to perceive. Out in the solar system, space is not a perfect vacuum. It's filled with a thin, electrically charged gas called plasma, which is the fourth state of matter. This plasma can carry waves of energy, not as the pressure waves we call sound, but as electromagnetic vibrations, and our robotic explorers, like the Voyager and Cassini spacecraft, were equipped with instruments specifically designed to detect these ripples. When scientists translate this captured data into frequencies our ears can hear, the results are nothing short of haunting. From the realm of Jupiter, we hear the ghostly chorus of its immense magnetic field, a cacophony of shrieks, whistles, and pops created by charged particles racing along the gas giant's powerful magnetic field lines. It sounds like a cosmic wind whipping through a celestial forest, or the melancholic song of a long-lost world. Saturn contributes its own otherworldly melody, a series of eerie, pulsing radio emissions that ebb and flow with the planet's rotation, a rhythmic heartbeat from a world a billion kilometers away. This process of converting non-audio data into sound is known as data sonification, and it has become a powerful tool for scientific discovery. It allows researchers to hear patterns in complex information that might be difficult to spot with graphs and numbers alone. They can listen to the solar wind buffeting a planet's magnetic bubble or the subtle vibrations of a distant star. We can even hear the cataclysmic ripples in spacetime from colliding black holes, translated into a distinct chirp that mark the first direct detection of gravitational waves. So the next time you look up at a quiet, star-filled night, remember that the stillness is an illusion. You are simply surrounded by a symphony playing in a key your ears haven't learned to hear, a chorus of plasma waves, magnetic storms, and stellar vibrations that reveals a universe that is not silent, but is perpetually and magnificently singing. Leaving behind the ghostly symphonies of space, we arrive at a world that seems ripped straight from the pages of a cosmic fairy tale. Imagine a planet not of rock, iron, or gas, but one that is quite literally a jewel of unimaginable value. Meet 55 Cancri, an exoplanet orbiting a star 41 light-years away, a world so exotic that scientists are confident a vast portion of its interior is composed of crystallized diamond. This isn't science fiction, it's the conclusion drawn from rigorous astronomical detective work. The story of this diamond planet begins with its origins. The star it orbits, 55 Cancri, is part of a binary system and is unusually rich in carbon, the very element that forms the basis of diamond. When the planetary system was forming, this abundance of carbon acted as the primary building block for the planets around it. Astronomers believe that 55 Cancri is the remnant core of a gas giant that migrated too close to its sun, having its thick atmosphere of hydrogen and helium violently stripped away by the star's intense heat and radiation. What remained was a super-Earth, a rocky world with about twice Earth's diameter and over 8 times its mass, composed predominantly of carbon. Now, Place this massive ball of carbon under the kind of conditions found on 55 Cancri. It orbits so close to its host star that a single year, one complete orbit, takes less than 18 hours. Surface temperatures are thought to soar to a blistering 2,400 degrees Celsius, hot enough to melt iron. More critically, the immense gravitational pressure from the planet's own mass, combined with the searing heat, creates the perfect alchemical furnace. Deep within its interior, pressures are so extreme that they force the carbon atoms to arrange themselves into the rigid, crystalline structure we know as diamond. It's estimated that up to a third of the planet's interior, a layer thousands of miles thick, could be a glittering diamond lattice. How did astronomers piece together this incredible picture? They never directly saw the diamond, of course. The discovery was made using the powerful tools of spectroscopy and planetary modeling. By carefully analyzing the light from the host star as the planet transited or passed in front of it, scientists could detect subtle chemical signatures in the starlight that filtered through any hypothetical atmosphere. The data pointed overwhelmingly to a carbon-rich, oxygen-poor environment. In a system with more carbon than oxygen, the carbon atoms are free to bond with each other rather than forming silicon-based rocks like those on Earth. With this chemical blueprint in hand, researchers then applied models of planetary formation and interior physics. They calculated that given the planet's known mass, radius, and immense internal heat and pressure, the carbon could not exist as graphite or other forms. The only stable structure under such hellish conditions would be diamond. Artists' impressions of this world are as breathtaking as they are terrifying. Picture a dark, rocky landscape glowing with a dull red heat from the nearby star, which would appear enormous in the sky. But beneath this scorched crust lies a planetary mantle of pure diamond, possibly with a molten carbon core at its center. Some theories even suggest that the extreme conditions could create carbon rain or rivers of tar on the surface, but the true treasure is buried deep within. This glittering world forces us to expand our definition of what a planet can be. Our own solar system is built on oxygen and silicon, giving us rocky worlds and gas giants. But 55 Cancri is a stark reminder that around other stars, with different elemental recipes, nature can forge worlds of breathtaking and almost unimaginable composition. It is a testament to the universe's boundless creativity, capable of crafting a celestial diamond from the ashes of a lost giant. While we have marveled at worlds of diamond and heard the songs of planets, here in our own cosmic backyard lies a testament to human achievement preserved with almost supernatural perfection. The footprints left by the Apollo astronauts on the lunar surface are not just historical artifacts, they are potentially eternal marks on a world where time itself seems to stand still. Unlike on Earth, where a footprint on a beach is washed away by the next tide or scattered by the wind within hours, those iconic impressions in the lunar regolith could remain perfectly intact for millions of years. The reason for this incredible permanence boils down to the Moon being a world in a state of profound geological stillness. It lacks the three great erasers that constantly reshape the face of our own planet: an atmosphere, liquid water, and active plate tectonics. There is no wind to whisper across the plains and gently fill the prints with dust. There are no rains to fall and wash them away, no rivers to carve new channels, and no oceans to create tides that would slowly grind the fine soil into something new. Beneath the surface, the Moon's internal engine has largely cooled and shut down, meaning there are no volcanic eruptions to bury the sites under layers of fresh lava and no shifting continental plates to crumple the landscape. The only force of change on the Moon is an incredibly slow and patient one, the relentless rain of micrometeorites. These are tiny specks of cosmic dust, most no larger than a grain of sand, that strike the lunar surface at tremendous speeds. Over timescales that dwarf human history, this gentle, constant sandblasting will eventually act like a cosmic eraser, gradually churning the top layer of the soil in a process known as gardening. But this is a process that takes millions, even tens of millions of years to significantly alter the landscape. To understand the scale, imagine a single footprint left in soft soil. On Earth, it might be gone in a week. On the Moon, that same footprint will likely remain crisply defined for 10 million years, a silent monument long after the civilizations that created it have transformed beyond recognition. When you see those iconic images of Buzz Aldrin's boot print, with its clear tread pattern set against the fine, gray powder, you are looking at what is arguably humanity's most enduring mark on any world. The pyramids of Egypt will eventually crumble to sand, and the steel of our greatest cities will rust away, but those steps in the Sea of Tranquility will outlast nearly every structure and artifact we have ever built on our active, living planet. They are a poignant reminder of our fleeting moment of exploration, frozen in time on a world that faithfully keeps our record, moving from the silent, preserved history on our moon to our own dynamic star. We encounter a puzzle that has baffled the greatest minds in physics for nearly a century. It's a mystery that defies our most basic intuition about heat and energy, a paradox playing out in plain sight every single day. The surface of the sun, the photosphere, is what we see as its brilliant, yellow-white disk. It's a roiling sea of incandescent plasma with a temperature of around 5,500 degrees Celsius, which is hot enough to vaporize any substance known to humanity. But if you were to travel upwards from this inferno, away from the sun's core where nuclear fusion rages, you would expect the temperature to drop, right? Just as the air gets colder the higher you climb a mountain, astonishingly, the opposite happens. As you move into the sun's outer atmosphere, a wispy, shimmering halo called the corona, the temperature doesn't fall, it skyrockets, soaring to an unimaginable 1 to 2 million degrees Celsius. This is the coronal heating problem, and it's as if you walked away from a blazing fire only to find yourself suddenly engulfed in flames 1,000 times hotter. Scientists first confirmed this bizarre temperature inversion during solar eclipses when the moon perfectly blocks the sun's blinding disk, revealing the delicate, pearly white corona. The light from the corona has a specific spectral signature that indicates its constituent particles are moving at velocities consistent with these multi-million-degree temperatures. The question is simple and profound: what is the furnace that is heating this distant, tenuous atmosphere to such extraordinary levels? One of the most promising explanations lies in the sun's incredibly complex and dynamic magnetic field. The sun is not a solid ball, it's a fluid plasma, and different parts of it rotate at different speeds. This churning motion tangles and stresses the magnetic field lines that are anchored deep within the star, like twisting a rubber band until it suddenly snaps. This magnetic stress can be released in two primary ways. The first is through colossal, explosive events we can see, like solar flares and coronal mass ejections. But scientists now believe the real key might be in events too small for us to directly observe. These are called nanoflares. The theory suggests that the sun's magnetic field is constantly, quietly reconnecting and releasing tiny bursts of energy all across the corona. Individually, each nanoflare is minuscule, but collectively, they act like a million microscopic lighters being flicked on every second, providing a continuous, distributed heat source that could explain the corona's staggering temperature. Another compelling theory points to magnetic waves. The sun's convective interior is a constant thunder of acoustic and magnetic vibrations, like a colossal, resonating bell. These vibrations travel upwards along the magnetic field lines that thread through the solar atmosphere. As these waves move out into the rapidly thinning corona, their energy becomes concentrated, and they can break like ocean waves on a shore, dumping their tremendous energy into the surrounding plasma and heating it to extreme temperatures. It's likely that both of these mechanisms, along with others we have yet to discover, are working in concert to solve this cosmic conundrum. Spectacular footage from satellites like the Solar Dynamics Observatory brings this invisible magnetic drama to life. We can see vast, arching loops of incandescent plasma, each one a visible trace of a magnetic field line, glowing at over 1,000,000 degrees. We witness solar flares erupting with the power of millions of hydrogen bombs, and we can observe the corona itself streaming outwards as the solar wind, a 1,000,000-degree breeze that washes over the entire solar system. This isn't just an academic curiosity. Understanding the coronal heating problem is crucial for space weather forecasting. The energy that heats the corona also drives the solar wind and solar storms, which can disrupt satellites, knock out power grids on Earth, and pose a radiation hazard to astronauts. So this fundamental mystery of physics is also a very practical one, reminding us that the sun is not a placid, constant ball of light, but a seething, dynamic, and magnificently complex star, whose most profound secrets are hidden in the ghostly, superheated halo that crowns its fiery face. Now, journey from the superheated atmosphere of our sun to a world that, against all odds, harbors one of the most precious resources in the universe, hidden in the most unexpected of places. If I told you there is a planet where surface temperatures are hot enough to melt lead during the day, yet it possesses vast stores of water ice, you might assume we've traveled to the outer solar system. But this world is Mercury. The closest planet to the Sun is, paradoxically, an ice world at its poles. This discovery completely upends our traditional view of the solar system's thermal map and reveals a clever trick of planetary geometry. The secret lies in Mercury's posture. Unlike Earth, which has a significant axial tilt of about 23.5 degrees that gives us our seasons, Mercury is barely leaning over at all. Its rotational axis is almost perfectly perpendicular to its orbit around the Sun. This means that the rims of certain craters at its north and south poles cast permanent, unyielding shadows over their floors. Inside these deep polar craters, the Sun never rises. It is a darkness that has persisted for billions of years, a profound and eternal cold trap, while the sunlit surfaces of Mercury bake at a scorching 430 degrees Celsius. The temperatures in these permanently shadowed regions can plummet to a bone-chilling -200 degrees Celsius. It is within these frigid, sunless pockets that water ice, delivered by comets and asteroids over the eons, has found a permanent home, preserved as if in a cosmic deep freeze. The first tantalizing hints of this ice emerged not from visual images, but from radar. In the 1990s, astronomers using the massive Arecibo radio telescope in Puerto Rico aimed powerful radar signals at Mercury. To their astonishment, the signals that bounced back from the polar regions showed a signature that was incredibly bright and highly reflective, precisely matching the radar characteristics of water ice. It was as if someone had placed giant mirrors at the planet's poles. The definitive confirmation, however, came from a spacecraft that got up close and personal with this enigmatic world. NASA Messenger Orbiter, which studied Mercury from 2011 to 2015, employed a suite of instruments to prove the case. Its neutron spectrometer detected a telltale signature of hydrogen, a key component of water, concentrated in those same polar craters. Furthermore, by carefully mapping the topography and illumination of the poles, Messenger Laser Altimeter confirmed that these hydrogen-rich deposits were located exclusively in areas of permanent shadow. Some of these ice reservoirs are covered by a mysterious, dark layer of complex organic material, which likely acts as an insulating blanket, protecting the pristine ice beneath from the occasional effects of micrometeorite bombardment or the tenuous solar wind. The implications of this discovery are staggering. It tells us that water, that vital ingredient for life as we know it, is not the exclusive property of the outer, colder solar system. It can survive even in the most hellish and seemingly inhospitable environments, provided there is a safe harbor. This fundamentally changes our understanding of how water was distributed throughout the early solar system. The inner planets were likely bombarded by water-rich comets and asteroids in their youth, a period known as the Late Heavy Bombardment. On a world like Earth, with its active geology and atmosphere, much of this water was incorporated into the oceans and the crust. On a geologically dead world like the Moon or Mercury, with no atmosphere to speak of, the water would normally be lost to space unless it landed in one of these perfectly positioned, permanently cold traps. Finding ice on Mercury makes the presence of water on our own moon, and potentially in the shadowed craters of other airless bodies, seem far less surprising. It paints a picture of a solar system that was, from its very beginning, wetter and more resource-rich than we ever imagined, with water managing to find a foothold in the most improbable and hostile of corners. Shifting our gaze from the scorching inner solar system to the realm of the giants, we encounter a tempest so vast it has been raging for centuries, a swirling crimson eye that has watched over the solar system since the time of Galileo. This is Jupiter's Great Red Spot, an anticyclonic storm that is both a monument to planetary power and a puzzle in slow motion, because this legendary feature, large enough to swallow our entire planet, is now steadily and mysteriously shrinking. For as long as we have had telescopes powerful enough to see it, the Great Red Spot has been a constant, churning presence in Jupiter's southern hemisphere. Its observed history stretches back to at least the 1600s, with early astronomers like Giovanni Cassini noting a permanent spot on the face of the gas giant. For centuries, it was a truly colossal feature, with historical records suggesting it may have once been wide enough to fit 3 Earths side by side. It is a storm of unimaginable ferocity, with winds at its outer edges screaming at speeds exceeding 430 kilometers per hour, yet, despite this perpetual fury, the storm is not eternal. Modern observations, particularly from workhorse observatories like the Hubble Space Telescope, have documented a clear and persistent trend: the Great Red Spot is getting smaller. Time-lapse animations compiled from decades of Hubble images tell a dramatic story of contraction. The once oval storm is becoming more circular, and its longitudinal extent has diminished significantly. Where it once measured about 40,000 kilometers across at its widest in the late 19th century, it is now a comparatively compact 16,000 kilometers, still large enough to engulf Earth, but a shadow of its former self. The reasons for its incredible longevity are rooted in the very nature of Jupiter itself. Unlike storms on Earth, which are powered by the sun's heat and quickly run out of energy once they move over land or cool water, the Great Red Spot is a self-sustaining system. Jupiter is a world with no solid surface to disrupt its flow. It is a deep, churning ball of hydrogen and helium. The storm draws its energy from the planet's own internal heat, left over from its formation and released slowly over billions of years. This internal furnace drives violent convection currents, pushing hotter gas from the interior up to the cloud tops, where it cools and sinks again. The Great Red Spot acts like a massive planetary gear, tapping into these vertical currents and the planet's rapid rotation. A day on Jupiter is a mere 10 hours long to maintain its swirling momentum. It is essentially a stable, high-pressure vortex that has been spinning for so long because it is plugged directly into Jupiter's own energetic heart. So why, after centuries of stability, is it now shrinking? This is where the mystery deepens, and scientists are actively investigating several compelling theories. One idea suggests that the storm's contraction is a natural part of its life cycle, perhaps triggered by interactions with smaller eddies and jets that stream through Jupiter's complex atmospheric bands. These smaller storms could be acting like cosmic Pac-Men, nibbling away at the edges of the giant vortex and disrupting its flow, stealing some of its energy and momentum. Another fascinating possibility involves the storm's own internal dynamics. As the Great Red Spot shrinks, its spin rate should theoretically increase, much like an ice skater pulling their arms in to spin faster. This accelerated rotation might be changing how the storm interacts with the surrounding atmospheric currents, potentially causing it to shed mass or energy more efficiently, which in turn fuels further shrinkage. There is also the question of whether we are witnessing a temporary fluctuation or an irreversible decline. Some computer models indicate that the storm might go through cycles of growth and decay, and that it could potentially stabilize at a new, smaller size. Others suggest that the changes in Jupiter's global wind patterns and temperature gradients, which we are only beginning to map in detail, are creating an environment that is less hospitable for such a gigantic storm to sustain itself. The ultimate fate of the Great Red Spot remains one of the solar system's great open questions. Will it continue to shrink until it vanishes entirely within the next few decades, or will it find a new equilibrium and persist as a smaller, but still formidable, feature for another century? Every new image from Hubble and every date a transmission from probes like Juno brings us closer to understanding the complex atmospheric physics at play. Watching this slow-motion transformation is a humbling reminder that even the most permanent-looking features in our cosmic neighborhood are dynamic and transient, participants in an endless celestial dance of creation and dissolution happening right before our eyes. After exploring the silent, eternal footprints on the Moon and the shrinking fury of Jupiter's Great Red Spot, let's turn our attention to a celestial object that proves some of the most scientifically valuable things in the universe can also be the smelliest. When the European Space Agency's Rosetta spacecraft finally caught up with Comet 67P, Churyumov-Gerasimenko, after a 10-year chase, it didn't just send back stunning images of a craggy, duck-shaped world. Its onboard instruments also took a deep, metaphorical sniff of the comet's surrounding atmosphere, or coma. The resulting chemical analysis was, to put it mildly, an assault on the senses. The Rosetta mission detected a complex and pungent cocktail of gases, a veritable perfume of primordial origins. Among the most notable ingredients were hydrogen sulfide, which carries the unmistakable and revolting aroma of rotten eggs, ammonia, which has the sharp, acrid smell associated with horse stables and cleaning products, and formaldehyde, a pungent preservative. If you could somehow take a breath near this cosmic iceberg as it swung around the sun, the experience would be overwhelmingly foul, a bizarre blend of a barnyard, a chemistry lab, and a forgotten roadside egg. But why is this cosmic stench so incredibly important? It turns out that these smelly molecules are not contaminants or signs of decay. They are pristine time capsules, frozen relics from the very dawn of our solar system over 4.6 billion years ago. Comets like 67P are thought to be ancient leftovers from the planet-forming process, icy planetesimals that were flung out to the cold, dark fringes of the solar system in the Oort cloud and the Kuiper belt. Out there in the deep freeze, their chemical composition has remained almost entirely unchanged since their formation. The hydrogen sulfide, ammonia, formaldehyde, and other detected compounds like hydrogen cyanide, which smells of bitter almonds, are therefore a direct sample of the original ingredient list from which the entire solar system was built. This smelly cloud is the raw material from which the Sun, the Earth, and ultimately we ourselves were constructed. Every time you smell a rotten egg on Earth, you are encountering a molecule that was a fundamental building block of our cosmic neighborhood. The Rosetta mission's findings provide powerful support for the theory that comets played a crucial role in seeding the young Earth with the volatile compounds and organic molecules necessary for life. The very water in our oceans and the carbon-based chemistry that makes life possible may have been delivered, in part, by these smelly, icy messengers from the outer solar system. So, while we might crinkle our noses at the thought, this cosmic stench is actually the scent of our own creation, a pungent reminder that the universe's most profound gifts don't always come in the most pleasant packages. Now, let's bring this cosmic perspective right back down to Earth with a fact that beautifully connects the familiar world beneath our feet to the grand expanse above our heads. We often think of our planet as a small, fragile blue marble in a vast cosmic ocean, dwarfed by the unimaginable scale of the galaxy it calls home. But here is a humbling and perspective-shifting truth. On our one single planet, there are significantly more trees than there are stars in our entire Milky Way galaxy. Let's put some staggering numbers to that claim. Thanks to a massive, collaborative scientific effort involving satellite imagery and ground surveys across the globe, ecologists have estimated that Earth is home to over 3 trillion trees. That's a 3 followed by 12 zeros. Meanwhile, astronomers, using sophisticated stellar population models and observations from telescopes like Hubble, estimate that our Milky Way contains somewhere between 100 billion and 400 billion stars. Even if we take the highest estimate for the stars and the lowest for the trees, our planet's forests still outnumber the galaxy's suns by a wide margin. To truly grasp the scale of 3 trillion, imagine giving every single person on Earth a personal forest of 400 trees. That's the kind of abundance we're talking about. The method for counting trees is a marvel of modern science in itself. It isn't just about looking at satellite photos and guessing, it's a complex process of fusion. Satellites provide the broad overview, mapping the entire planet's land cover and identifying forested areas, but to get an accurate count, scientists combine this orbital data with thousands of painstaking ground surveys. Teams on the Earth physically measure and count trees in sample plots, and this boots-on-the-ground truth is used to calibrate the computer models that then extrapolate the total number from the satellite imagery. It's a global census of life, and the result is a number so large it challenges our understanding of our own world. On the galactic side, counting stars involves a different kind of cosmic detective work. We can't simply take a picture of the Milky Way and count every pinpoint of light. Our view is obscured by vast clouds of interstellar dust, and we are embedded within the galaxy's disk itself. Instead, astronomers measure the galaxy's total mass and its structure, and then use our understanding of stellar evolution to build a model of how many stars of different sizes and brightnesses it likely contains. They survey representative regions in great detail and then extrapolate those findings to the galaxy as a whole. The result is that magnificent range of 100 to 400 billion stellar furnaces. This comparison is not meant to diminish the grandeur of the cosmos, but to profoundly elevate our appreciation for the incredible, buzzing, thriving biological richness of our own world. Our planet is not just a speck of rock and water, it is an oasis of almost incomprehensible vitality. Every one of those 3 trillion trees is a complex living organism, breathing in carbon dioxide, breathing out oxygen, providing habitat, stabilizing soil, and contributing to the great engine of Earth's biosphere. Each is a tiny world unto itself, while a star is a colossal and often solitary nuclear reactor. This fact reframes our place in the universe. We are not inhabitants of a minor, insignificant world, but of a planet that is, in its own way, bursting with more tangible, intricate complexity than the entire vast collection of suns that make up our galactic home. It's a powerful reminder that while we gaze upward in search of cosmic wonders, we are already living on one of the most spectacularly abundant and diverse islands of life we could ever hope to find. But while some cosmic phenomena unfold over billions of years, others can have a dramatic and immediate effect on the human body, reshaping it in ways that sound almost like science fiction. Here on Earth, gravity is a constant, compressive force pushing down on you from the moment you're born and subtly sculpting your skeleton over a lifetime. But take that force away, and your body responds in some truly bizarre ways. One of the most visually striking changes astronauts experience in the microgravity of space is that they actually get taller, temporarily gaining up to 2 inches in height. This cosmic growth spurt isn't due to any magical elixir or alien radiation. It's a simple matter of mechanical relief for your spine. Your spinal column isn't a single, solid bone. It's a stack of vertebrae separated by soft, gel-filled cushions called intervertebral discs. These discs act as shock absorbers for your body. Under the constant pull of Earth's gravity, these discs are perpetually compressed, squeezed flat throughout the day, which is why you might find you're slightly shorter by evening than you were when you woke up. In the weightless environment of orbit, that compressive load simply vanishes. Freed from the burden of gravity, the spongy discs between your vertebrae expand and rehydrate, like compressed kitchen sponges being allowed to puff up to their full volume. This expansion pushes each vertebra slightly farther apart from its neighbors, spread over the entire length of the spine, from the neck down to the pelvis. This tiny added space at each joint adds up to a significant increase in overall height, typically around 3%. For a 6-foot-tall astronaut, that translates to a gain of over 2 inches, a change that is immediately noticeable to the crew and is carefully measured by flight surgeons. However, this newfound height comes with a significant and often painful downside. The same stretching of the spine also lengthens and tightens the muscles and ligaments that run along the vertebral column. Without gravity to provide resistance, the back muscles, accustomed to constantly working to support your posture on Earth, begin to weaken and atrophy. This combination of a lengthened spine and weakened support structure is a recipe for intense back pain, a complaint so common among astronauts it's been informally dubbed space back. Many crew members report a persistent, dull ache, similar to the discomfort you might feel after a long day of poor posture, but lasting for weeks or even the entire duration of their mission. The real challenges, however, often begin when they return to Earth. Coming home is a violent reintroduction to gravity's embrace. That elongated spine, no longer supported by strong muscles, is now subjected to the full compressive load once again. The expanded discs are brutally squeezed back down, and the weakened musculature struggles to stabilize the vertebral column. This can lead to a high risk of spinal injuries, such as herniated discs, in the days and weeks following a mission. Astronauts have to be carefully lifted from their spacecraft upon landing, and they undergo extensive physical rehabilitation to rebuild the core strength needed to support their spines under the renewed force of gravity. Before and after medical scans provide a stark visual of this transformation. Magnetic resonance imaging, or MRI, images of an astronaut's spine taken before launch and then again after a few weeks in orbit show a clear and dramatic lengthening of the spinal column with visibly increased spaces between the vertebrae. These images look less like a before and after comparison and more like 2 different spines altogether. Then, post-landing scans show the rapid recompression as the body readapts to its home planet. This entire cycle is a powerful reminder that human physiology is exquisitely fine-tuned for life on Earth. We are creatures of gravity, and when we step off our world, even our most fundamental structures, the very bones in our backs, respond in ways we are only beginning to fully understand. While we marvel at the preserved footprints on our moon and the shrinking storm on Jupiter, Mars presents us with a monument of a different kind, a mountain so vast it redefines the very meaning of the word. Welcome to Olympus Mons, the single largest volcano in our entire solar system. This is not merely a mountain, it is a geological titan, a shield volcano that stands an almost incomprehensible 22 kilometers or 13.6 miles high. To put that staggering scale into perspective, that is nearly 2.5 times the height of Mount Everest above sea level, but its true immensity isn't just in its height, it's in its footprint. The base of Olympus Mons sprawls across an area roughly the size of the entire state of Arizona, a colossal, gently sloping ramp that dominates the Martian landscape. If you were standing on its summit, the peak would be so far above the surrounding plains that the curvature of the planet itself would be visibly apparent, and the volcano's flanks would stretch all the way to the horizon in every direction, creating the illusion that you were standing on a world all by itself. The formation of this behemoth is a direct consequence of two fundamental differences between Mars and Earth: its lower surface gravity and its silent, stagnant interior. Mars has only about 38% of Earth's gravity, meaning that the pull holding everything to the planet is much weaker. This allowed volcanic lava to flow much farther and build up much thicker layers before solidifying, creating those characteristically broad, gently sloping sides that define a shield volcano. But the real secret to Olympus Mons' unparalleled size is the absence of plate tectonics. Here on Earth, our planet's crust is a jigsaw puzzle of moving tectonic plates. As a volcanic hotspot feeds magma to the surface, the plate slowly drifts over it. This creates a chain of volcanoes, like the Hawaiian Islands, where each island is a separate volcano that formed and then was carried away from the hotspot as the Pacific plate moved northwest. Mars, however, lacks this mobile crust. Its tectonic plates are locked in place, frozen solid for billions of years. This meant that when a massive plume of hot magma rose from the Martian mantle, it remained fixed in one location, pouring lava onto the same spot continuously, layer upon layer, for perhaps billions of years. Without any crustal movement to shift the volcanic output to a new location, the volcano just kept growing and growing, amassing a volume that is 100 times greater than that of Mauna Loa in Hawaii, the largest volcano on Earth. Imagine a single geological fountain erupting relentlessly in the same place for eons, patiently constructing a mountain that would dwarf every other feature in the solar system. The visual impact of this scale is best appreciated through breathtaking panoramic views, often rendered from orbital data collected by missions like NASA's Mars Reconnaissance Orbiter. In these images, the caldera, the complex of collapsed craters at the summit, is itself large enough to swallow entire cities, a sprawling depression over 80 kilometers wide. The cliffs that encircle the base of the volcano, known as the Olympus Mons Aureole, are sheer escarpments several kilometers high, evidence of colossal landslides as the mountain's own weight caused its flanks to collapse under the weak Martian gravity. Standing next to Mount Everest, Olympus Mons wouldn't just look taller, it would look like an entirely different class of object. Everest is a sharp, rugged peak thrust upwards by the collision of continents, a dramatic but localized feature. Olympus Mons is more like a continent in its own right, a vast, sprawling plateau that just happens to be a volcano. It is a permanent testament to a more violent, more energetic era in Mars's history, when its internal fires were still burning brightly and its geology operated on a scale we can scarcely imagine on our own dynamic, shifting planet. We've climbed the solar system's tallest volcano and felt the strange stretch of an astronaut's spine, but now we turn our attention to a class of cosmic objects so faint and mysterious that it blurs the very line between star and planet. Imagine, if you will, a star that isn't blazingly hot, a celestial body you could theoretically reach out and touch without being vaporized. This isn't science fiction, it's the reality of brown dwarfs, the universe's failed stars. Often called cosmic orphans, these objects form in much the same way as proper stars, from the collapse of a cloud of gas and dust, but they are born with a critical handicap: insufficient mass. For a star to shine with the brilliant, sustained fire of hydrogen fusion, the process that powers our sun and every other true star in the sky, it needs to achieve a critical internal pressure and temperature. This requires a minimum mass of about 8% of our sun's, or roughly 80 times the mass of Jupiter. Brown dwarfs fall tragically short of this mark, occupying a mass range between the heaviest gas giant planets and the lightest true stars. They are too massive to be considered planets, yet not massive enough to ignite the stellar engine in their core, leaving them in a perpetual state of cosmic adolescence. After their initial violent formation, they experience a brief, faint glow as they burn through a reserve of deuterium, a heavy isotope of hydrogen. But once that meager fuel is exhausted, there is no sustained hydrogen fusion to keep them hot. They don't die, they simply never truly live, embarking on a long, slow cooling journey into obscurity. It is this gradual loss of their initial heat of formation that leads to the most mind-bending property of the oldest and smallest brown dwarfs: their surface temperatures can be astonishingly mild. While our sun's surface rages at 5,500 degrees Celsius, the surfaces of the coolest known brown dwarfs, belonging to a spectral class whimsically named Y dwarfs, have been measured at temperatures below 100 degrees Celsius. That's cooler than a boiling pot of water. Some have been found with temperatures around 25 to 30 degrees Celsius room temperature. The very coolest of all, like Y's 0855-0714, discovered by NASA, a wide-field infrared survey explorer, is estimated to have a surface temperature of minus 23 degrees Celsius, colder than a winter day in Siberia. The concept is staggering: a star-like object, a ball of gas light years away, with a surface you could, in principle, rest your hand upon. Of course, you wouldn't actually want to try. While the temperature might be survivable, the environment around a brown dwarf would be utterly hostile. There's no solid surface to stand on. You would sink into a deep, turbulent atmosphere, likely rich in toxic gases like ammonia and methane, all under the crushing weight of immense gravity. And without the fierce stellar winds and radiation of a true star, their atmospheres might be calm enough for clouds to form not of water vapor, but of molten iron or sand, condensing out of the upper air and falling as bizarre, exotic rain. The true challenge with brown dwarfs isn't conceptual, it's finding them. They emit almost no visible light. In their youth, they glow a faint red in the infrared part of the spectrum, and as they age and cool, they become virtually invisible, emitting only the faintest heat signature. Detecting them requires incredibly sensitive infrared telescopes, like the Spitzer Space Telescope and the WISE mission. These observatories don't see the light we see, they see the heat these failed stars radiate as they slowly fade. The imagery used to represent them is often false color, translating invisible infrared data into a visible spectrum we can understand, painting these dark orbs in hues of magenta and deep red against the blackness of space. Their discovery has forced astronomers to create entirely new spectral classes, L, T, and Y, to categorize their unique atmospheric chemistry, which includes substances like water vapor, methane, and ammonia, molecules you would typically associate with planets, not stars. This is what makes them the perfect bridge between gas giants and stars. A massive gas giant like Jupiter and a low-mass brown dwarf can be nearly identical in size, but their internal lives are completely different. Jupiter radiates more heat than it receives from the Sun due to the slow contraction of its interior and the residual heat from its formation, but it was never close to triggering any form of fusion. A brown dwarf, however, did experience that brief, failed flash of deuterium burning, a last gasp before settling into its long, cooling twilight. They are the missing link, helping us understand the fine line that separates a planet from a star and proving that the universe is filled with objects that defy our simple, textbook categorizations. Now, let's travel from the failed stars and room temperature suns to the realm of the ringed giant, where a geometric marvel defies the very chaos of planetary weather. At Saturn's North Pole, a perfect gargantuan hexagon has been etched into the atmosphere, a six-sided cloud pattern so precise it looks as though it was drawn by the hand of a cosmic architect. This is not a fleeting arrangement of clouds, it is a persistent, towering jet stream that has been raging for decades, and possibly much longer, making it one of the most stunning and enduring meteorological wonders in our entire solar system. The story of its discovery is a tale of two robotic explorers. The Voyager spacecraft first glimpsed this bizarre feature in the 1980s as they flew past the gas giant, but their views were limited and from a distance, leaving scientists both intrigued and deeply puzzled. It wasn't until NASA Cassini mission arrived at Saturn in 2004 and began its long, detailed orbital tour that we were able to truly appreciate the hexagon's scale and complexity. Cassini's sophisticated cameras and instruments revealed a structure of almost unbelievable precision. Each side of the hexagon is wider than the diameter of Earth, and the entire structure is so vast that 4 Earths could comfortably fit inside it. This isn't a shallow surface feature, it's a deep-rooted atmospheric wave, a jet stream of air screaming along its path at speeds of around 320 kilometers per hour, with a colossal, rotating hurricane fixed directly at its center. Time-lapse videos compiled from years of Cassini observations are mesmerizing. They show the hexagon rotating with the planet's internal clockwork, completing one full revolution roughly every 10 hours and 30 minutes, which is Saturn's rotation period at depth. The cloud walls stream along the six-sided path like cars on an endless, celestial freeway, while the central vortex churns with its own violent energy. So, how does a turbulent, fluid atmosphere, governed by the same physics as our own, spontaneously generate such a perfect geometric shape? The answer lies not in alien construction, but in the elegant, if complex, dance of fluid dynamics. Here on Earth, we see simpler versions of this phenomenon in the laboratory. When a fluid of different densities is placed in a circular container and rotated at a certain speed, it can sometimes self-organize into stable polygonal shapes. The key is the difference in rotation speeds between different latitudes, a property inherent to all gas giants. Scientists believe that Saturn's hexagon is a manifestation of a standing wave pattern, a stable Rossby wave that has become locked into the planet's atmosphere. Think of it like a wave that gets trapped in a channel, bouncing back and forth without dissipating. On a spinning sphere, under the right conditions of wind shear and latitudinal variation, this wave can take on a polygonal form. The mathematics suggests that the number of sides is determined by the specific properties of the fluid flow, the speed of the jet, the planet's rotation rate, and the density gradients within the atmosphere. For Saturn's North Pole, the stable solution just happens to be a hexagon. Another compelling theory uses an analogy we can all understand, shaking a garden hose. If you take a loose, flexible hose and send a wave pulse down it, the hose can momentarily form a hexagon or other polygon as the wave reflects and interferes with itself. On a planetary scale, the jet stream acts like that hose, and the energy racing through it creates a stable, six-sided standing wave that pins the clouds into this incredible geometric path. What makes Saturn's hexagon even more special is its astonishing longevity. Storms on Earth, even the largest hurricanes, last for weeks. Jupiter's Great Red Spot has persisted for centuries. But a structured, polygonal jet stream of this scale and perfection is unknown anywhere else. Its stability suggests it is deeply anchored in Saturn's atmospheric circulation, a fundamental feature of the planet's weather engine that is immune to the smaller-scale turbulence that would quickly disrupt a similar pattern on Earth. The different possible explanations, the laboratory fluid experiments, the standing wave theory, the shaken hose analogy, all point to the same conclusion. The hexagon is a natural, if exceptionally rare, outcome of planetary fluid dynamics. It is a beautiful demonstration that the laws of physics, when played out on a giant canvas with the right ingredients, can produce art of the most sublime and mathematical kind. This giant, spinning snowflake at the top of Saturn is a permanent monument to the hidden order within apparent chaos, a reminder that even in the swirling maelstrom of a gas giant's atmosphere, the universe has a fondness for geometry. After contemplating the precise geometry of Saturn's hexagon and the faint glow of failed stars, you might expect the universe, in all its kaleidoscopic glory, to boast a color palette of unimaginable vibrancy. Yet when astronomers attempted to determine the ultimate, average color of everything we can see, the result was not a brilliant sapphire blue or a fiery crimson, but something far more domestic. If you were to blend the light from every star in every one of the hundreds of billions of galaxies across the observable universe into a single shade, you would get a pale, warm beige, a color officially named cosmic latte. This discovery emerged from a monumental scientific effort to take a true census of cosmic light. Researchers at Johns Hopkins University analyzed data from the 2-degree field galaxy redshift survey, which had meticulously cataloged the light from over 200,000 galaxies. Their goal was to create a definitive spectrum of the universe, a single rainbow that represented the combined energy output of all the stars shining in the surveyed galaxies. The process was akin to imagining every star in the cosmos, from the massive, brilliant blue giants to the small, cool red dwarfs, being placed into a colossal celestial blender. The resulting puree of light would contain every wavelength, from ultraviolet to infrared, but the key was determining which color our eyes would perceive if we could see this blended radiance all at once. To find the answer, the scientists had to translate the precise physical measurements of this composite spectrum into the standard color space understood by the human eye, accounting for how our retinas perceive different wavelengths of light. When they completed this cosmic calculation, the coordinates pointed to a specific and surprisingly muted point on the color wheel. The reason for this gentle beige hue lies in the demographics of the stellar population. The universe is not dominated by the flashy, short-lived blue stars or the faint, numerous red dwarfs alone. Instead, the most common stars by light output are middle-aged, yellow-white stars like our own Sun, which are in the most stable and long-lasting phase of their lives. These G-type and K-type stars emit light that peaks in the green-yellow part of the spectrum, but when their light is mixed with a significant contribution from the vast number of red dwarf stars and the smaller but potent input from blue giants, the various colors don't cancel each other out to make white. Instead, they combine to create a very specific off-white, a warm, creamy beige with just a hint of pinkish brown. The name Cosmic Latte was chosen in a public contest, capturing both the grandeur of the concept and the comforting, everyday nature of the color. Imagine holding a cup of coffee with just the right amount of milk stirred in. That soft, creamy tan is the official color of the entire observable universe. Visualizing this can be a powerful moment of perspective, an animation that starts with the in-sky blackness of space, then slowly fades in this gentle beige glow until it fills the screen, creates a striking contrast between the thrilling, colorful images of nebulae and galaxies we're used to and this underlying, fundamental hue of the cosmos. It serves as a humbling reminder that for all its violent explosions, swirling galaxies, and mysterious dark matter, the universe, on average, is a surprisingly calm and quiet place, painted in the most tranquil and ordinary of shades, the color of a quiet morning, the color of cosmic latte. Just when you thought 1 billion tons in a sugar cube from a neutron star was the ultimate expression of cosmic density, the universe presents us with another, more common, and in some ways even more extreme, state of matter. Consider the final, brilliant act of a star like our own Sun. After it exhausts its nuclear fuel, it will shed its outer layers in a beautiful planetary nebula, leaving behind its exposed, intensely hot core. This core is no longer generating energy through fusion. It is simply a blazing hot ember, a sphere of carbon and oxygen about the size of the Earth, but containing nearly all the mass the star originally had. This is a white dwarf, and the physics inside it is so bizarre that a single teaspoon of its material would weigh over 5 tons here on Earth, the equivalent of a full-grown African elephant compressed into the volume of a sugar cube. To grasp this, imagine taking all the matter that makes up a massive skyscraper, every steel beam, every concrete floor, every pane of glass, and crushing it down until it could fit inside a single teaspoon. That is the level of compression we are talking about. The force responsible for this incredible density is not the nuclear force that holds neutrons together in a neutron star, but a quantum mechanical phenomenon known as electron degeneracy pressure. In a normal star, the intense heat from fusion creates an outward pressure that balances the inward crush of gravity. When fusion stops, that supporting pressure vanishes, and gravity wins, compressing the star's core with unimaginable force. But electrons, which are fundamental particles, refuse to be squeezed too closely together due to the Pauli exclusion principle, a fundamental law of quantum mechanics that states that no two electrons can occupy the same quantum state. As gravity tries to crush the white dwarf, the electrons are forced into higher and higher energy states, creating a powerful outward pressure that halts the collapse. The result is a stellar corpse where matter exists in a state called degenerate matter, a form so dense that atoms themselves are crushed, the electrons are stripped from their atomic nuclei, creating a sea of free electrons moving through a lattice of atomic nuclei packed shoulder to shoulder. The atoms are so tightly pressed that their electron clouds are completely overlapping. The space that makes up over 99% of an atom on Earth is entirely squeezed out. This degenerate matter is incompressible. Adding more mass to a white dwarf does not make it larger, it only makes it denser and smaller, up to a critical limit. This leads to a fascinating and counterintuitive reality. The more massive a white dwarf is, the smaller its physical size becomes. A white dwarf with twice the mass of another isn't twice as big, it's actually smaller because the increased gravitational force crushes the degenerate core into an even more compact space. There is, however, a final limit to this compression, a point of no return known as the Chandrasekhar limit. If a white dwarf accrues enough mass, typically by pulling material from a companion star, to exceed about 1.4 times the mass of our Sun, the electron degeneracy pressure can no longer hold back gravity. At that moment, the star faces catastrophic collapse, either exploding in a Titanic-type Ia supernova or collapsing further into an even denser neutron star. This makes white dwarfs both stable endpoints for most stars and potential triggers for some of the most energetic explosions in the universe. The fate of our own Sun is written in this dense physics. In about 5 billion years, it will become a white dwarf, a fading, Earth-sized diamond in the void, slowly cooling over trillions of years into a cold, black lump of crystallized carbon, a cosmic cinder. When you look up at the Sun, you are looking at the future source of a planetary nebula and the eventual home of matter so dense that a fragment the size of a marble would outweigh an entire car. These stellar remnants are not rare oddities, they are the ultimate fate of over 97% of all the stars in our galaxy, including the one that gives us life, a silent and profound reminder that even in death, stars create states of matter that defy everything we know from our experience on Earth. While we've mapped the orbits of planets with incredible precision, there is growing and compelling evidence that our solar system's planetary census is incomplete. Lurking in the frigid darkness far beyond Neptune, a ghost may be haunting the outer reaches, a hypothetical giant world known as Planet 9. This isn't a mere hunch, it's a prediction born from the strange, clustered behavior of small, icy bodies in the distant Kuiper belt. The Kuiper belt is a vast disk of frozen leftovers from the solar system's formation, home to dwarf planets like Pluto and countless smaller objects. When astronomers began tracking the orbits of the most distant of these Kuiper belt objects, they noticed something deeply odd. Their orbits weren't randomly oriented as one would expect. Instead, they were mysteriously clustered, as if an unseen hand were herding them, their elongated paths all pointing in roughly the same direction and tilting in a similar way. This peculiar alignment is statistically incredibly unlikely to happen by chance. It's as if you dropped 100 pencils on the floor and they all landed pointing northeast. The most elegant explanation for this gravitational shepherding is the presence of a massive, yet to be detected planet. Based on the precise ways these distant orbits are being twisted and grouped, astronomers have calculated the probable characteristics of this hidden world. Planet 9 is hypothesized to be a super-Earth or a mini-Neptune with a mass roughly 5 to 10 times that of our own planet. Its orbit, however, would be wildly different from the near-circular paths of the 8 known planets. It's thought to follow a highly elliptical or oval-shaped path that takes it incredibly far from the Sun. At its closest approach, it might come within 200 to 300 astronomical units from the Sun, but at its most distant, it could swing out as far as 600 to 1200 astronomical units. To grasp that distance, consider that 1 astronomical unit is the distance from the Earth to the Sun. Pluto, by comparison, is only about 40 astronomical units away on average. This means Planet 9 would take an astonishingly long time to complete a single orbit, anywhere from 10,000 to 20,000 Earth years. The search for this cosmic phantom is one of the great modern detective stories in astronomy. Finding it is monumentally difficult because it would be incredibly faint, reflecting only the tiniest amount of sunlight from such an immense distance. Astronomers are using the world's most powerful telescopes, like the Subaru telescope in Hawaii, to systematically scan the vast swaths of sky where its predicted orbit might lie. They are looking for a single, slow-moving point of light against the background of fixed stars. Animated simulations bring this celestial hunt to life, showing the serene, orderly orbits of the known planets around the bright Sun, while far beyond, a swarm of small, icy objects trace their strange, clustered paths, all subtly orchestrated by the gentle, persistent gravitational pull of a single dark giant moving along its epic, lonely course. The existence of Planet 9 would not only rewrite our solar system's map, but also reshape our understanding of its formation, suggesting a dramatic past where planets were scattered and rearranged in ways we are only beginning to piece together. While our solar system might be hiding a distant, unseen giant, our entire galaxy is locked in an even grander and more certain cosmic dance with a predictable, spectacular finale. Far from being an isolated island universe, our Milky Way is gravitationally bound to its largest neighbor, the Andromeda Galaxy, and the two are currently racing toward each other at a breathtaking speed of about 110 kilometers per second. This isn't a random, catastrophic accident waiting to happen. It's a carefully choreographed merger set in motion by the mutual gravitational pull between these two colossal spirals. In approximately 4.5 billion years, they will begin a slow, majestic collision and eventual merger, a process that will fundamentally reshape our galactic home and create a new, larger galaxy often nicknamed millennia. The sheer scale of this event is almost beyond human comprehension. Andromeda, also known as Messier 31, is a titan containing an estimated 1 trillion stars, while our own Milky Way holds a comparatively modest 2 to 400 billion. When we look toward the constellation Andromeda on a clear, dark night, we can just barely make out a faint, fuzzy patch of light. That smudge is the combined glow of that trillion suns, located 2.5 million light-years away. And it is hurtling directly toward us. For a long time, the nature of this motion was uncertain. Was Andromeda on a mere glancing flyby, or was a direct impact in our future? The critical measurements came from NASA's Hubble Space Telescope, which meticulously tracked the sideways motion of Andromeda against the background of more distant galaxies. The data was conclusive. There is essentially no sideways movement. Andromeda is coming straight for us like a cosmic bullseye. The merger will not be a single, explosive event, but a drawn-out celestial ballet lasting billions of years. The first close pass will occur in about 4.5 billion years. From the vantage point of Earth, the approach would be a slow-motion spectacle of increasing grandeur. Over millions of years, the Andromeda galaxy would grow from a faint smudge into an ever larger and brighter spiral dominating the night sky. As it draws nearer, its delicate structure would become stunningly detailed, its spiral arms and dark dust lanes visible to the naked eye, eventually rivaling and then surpassing the full moon in apparent size. The night would become a truly two-galaxy affair. The actual collision is not what you might instinctively fear. The vast emptiness of space means that the stars within each galaxy are so widely spaced that direct stellar collisions are incredibly unlikely. The average distance between stars is so immense that you could think of it as two swarms of bees passing through each other. The individual bees rarely, if ever, touch. However, the interstellar gas and dust clouds within both galaxies will not be so lucky. These colossal clouds will slam into each other, compressing under the immense pressure and triggering a fireworks display of epic proportions, a massive burst of new star formation known as a starburst. The skies would be lit with the brilliant blue glow of countless newborn, massive stars and the pink hues of vast, newly ignited nebulae. The gravitational forces at play during this dance will be the real architects of destruction and creation. As the galaxies swing past each other on their first close encounter, their shapes will be violently distorted. Long, streaming tails of stars, gas, and dust will be gravitationally ripped away, flung out into intergalactic space like colossal tidal forces. Our familiar spiral Milky Way would be torn asunder, its beautiful pinwheel structure lost forever. The two galaxies will then swing back around, drawn together once more by their irresistible gravity for a second, and then a final merger. Over the next 1 to 2 billion years, they will gradually settle down, their stars and remaining gas relaxing into a new, stable configuration. The final product, millennia, will likely be a giant elliptical galaxy, a featureless, football-shaped swarm of stars, a testament to a turbulent and violent past. The fate of our solar system in this cosmic upheaval is a fascinating question. While our planet itself is in no danger of being struck, its orbit around the Sun could be significantly altered. Simulations suggest there's about a 50% chance that our solar system could be flung much farther out into the galactic halo of the new elliptical galaxy, and a 12% chance that we could be entirely ejected into the intergalactic void. Yet, even if we were cast out, the night sky from Earth would still be filled with stars, as we would take all the nearby stars of our original galactic neighborhood with us. The real showstopper would be the view. Computer simulations, based on the known laws of physics, provide a breathtaking preview of this event. They show the two distinct spiral disks first approaching, then gracefully passing through one another, their structures stretching and warping into long, brilliant bridges and shells. The cores of the two galaxies, each containing a supermassive black hole, will eventually sink to the center of the new system through a process called dynamical friction, where they will orbit each other and, in time, merge themselves, releasing ripples in spacetime known as gravitational waves. These visualizations transform this billions of years process into a captivating cosmic movie, a dance of gravity on the grandest possible stage. This inevitable future collision forces a profound shift in perspective. We often think of galaxies as immutable, permanent fixtures in the cosmos, but they are dynamic, evolving systems, growing and changing through these very mergers. The Milky Way itself is a product of past, smaller galactic acquisitions, and the formation of Milkdromede is simply the next chapter in its life story. It's a humbling and awe-inspiring reminder that the universe is in a constant state of flux, with entire galaxies serving as players in an endless, graceful, and occasionally violent dance. But if you think a planet of diamond is extreme, wait until you encounter a world where the skies rain daggers. Welcome to HD 189733b, a hot Jupiter located 64 light-years away in the constellation Vulpecula. This planet takes the concept of harsh weather and elevates it to a truly terrifying and lethal art form. Imagine a world of deep, cobalt blue, a color that from a distance might evoke the tranquil oceans of Earth. But this azure hue is not from water, it is the signature of an atmosphere hazy with silicate particles, and on this world, those particles don't just float, they fall in a relentless, horizontal tempest of molten glass. The conditions on HD 189733b are the stuff of nightmares, forged by its intimate and deadly relationship with its host star. It is what astronomers call a hot Jupiter, a gas giant that orbits astonishingly close to its sun, so close, in fact, that a single year, one complete orbit, takes just 2.2 Earth days. This proximity locks the planet in a gravitational embrace so tight that one side likely faces the star permanently, broiling under endless daylight, while the other is plunged into eternal night. The temperature difference between these two hemispheres is staggering, with the day side reaching a furnace like 900 degrees Celsius. This extreme thermal inequality is the engine that drives the planet's most famous feature, supersonic winds. To redistribute the immense heat from the day side to the night side, the atmosphere convulses with wind speeds that are estimated to reach up to 5,400 miles per hour. That is more than 7 times the speed of sound here on Earth, a gale so powerful it would not just knock you over, it would tear you apart molecule by molecule. Now add the main ingredient to this atmospheric hellbroth, silicon. Using the Hubble Space Telescope, astronomers performed a remarkable feat of remote sensing. They didn't take a direct picture of the planet. Instead, they watched carefully as HD 189733b passed behind its star, an event known as a secondary eclipse. By measuring the tiny dip in the total light from the star system before, during, and after the planet disappeared from view, they could isolate the specific light signature coming from the planet itself. When they analyzed this light using spectroscopy, They found the telltale signature of silicate particles in the atmosphere. On Earth, silicates are the minerals that make up sand and quartz. But in the scorching, high-altitude layers of this planet's atmosphere, these silicates exist as tiny, vaporized particles. The dramatic weather cycle is both beautiful and brutal. As these silicate vapors are blown from the scorching dayside into the slightly cooler terminator region, the line between day and night, they condense. But they don't form pleasant raindrops. In that searing heat and turbulent environment, they crystallize directly into tiny, razor-sharp shards of glass. And then, propelled by those 5,000-mile-per-hour winds, this glass rain doesn't fall gently downward. It flies sideways, scouring the landscape in a perpetual, abrasive hurricane. Artists' concepts of this world are as stunning as they are fearsome. Picture a deep blue marble set against the blackness of space, its parent star looming large and angry in the sky. The surface, if there is one beneath the thick atmosphere, would be a blasted hellscape, constantly polished by this hyperkinetic sandblasting. The very clouds in the sky might glow with a faint, menacing light, and the horizon would be a perpetual, violent storm of flying crystalline daggers. This isn't just a wild speculation, it's a robust conclusion based on physical laws and direct observation. The detection of silicates, combined with the measured temperature profile and modeled wind speeds, paints a consistent and terrifying picture. It's a world that showcases the incredible diversity of planetary environments, a place where the very same elements that form beautiful beaches on Earth are forged into a weapon of atmospheric fury. HD 189733b stands as a stark monument to the fact that the universe is not always a welcoming place, capable of creating realms of such extreme and lethal beauty that they defy our most vivid imaginations. But while the footprints on the lunar surface remain perfectly still, the moon itself is far from a dead, silent world. It has a heartbeat, a subtle seismic rumble that tells a story of a world that is still cooling, still settling, and still being pelted by its cosmic past. We know this because between 1969 and 1972, Apollo astronauts left behind a network of 4 sophisticated seismometers at their landing sites. These instruments faithfully recorded the lunar shutters for 8 years, painting a picture of a surprisingly active world and revealing 4 distinct types of moonquakes, each with its own unique origin and tale to tell. The most common and the deepest of these are the deep moonquakes, occurring roughly 700 kilometers below the surface. These aren't random events, they are meticulously scheduled, triggered by the same gravitational pull that gives our oceans their tides. As the moon orbits Earth, our planet's gravity tugs and flexes the entire lunar globe, creating stress that is released in these rhythmic, low-magnitude tremors. They are the moon's gentle, internal response to our cosmic dance, happening with such predictable regularity that scientists could practically set their watches by them. Then there are the much rarer, but far more powerful, shallow moonquakes, originating only 20 to 30 kilometers deep. These can register up to 5.5 on the Richter scale, a tremor strong enough to cause significant damage to any future lunar base. A quake of that magnitude on Earth would be felt over a large area and could crack walls. The cause of these powerful, infrequent events remains one of the moon's biggest mysteries, but the leading theory points to tectonic activity, the shifting and sliding of fault lines in the lunar crust as the entire moon slowly contracts. You see, the moon is still losing the heat from its formation, and as its interior cools, it shrinks, like a grape wrinkling into a raisin. This global contraction causes the brittle outer crust to crack and thrust over itself, creating lobate scarps, cliff-like faults that scientists have spotted all across the lunar surface. Every time one of these faults slips, it releases pent-up energy as a shallow moonquake, a stark reminder that the moon is a geologically evolving world. The third type of moonquake is the most predictable of all, driven by the most extreme temperature swings in the entire solar system. For 14 days at a time, the lunar surface bakes in unfiltered sunlight, with temperatures soaring to 120 degrees Celsius. Then, for an equal 14 days, it plunges into the utter darkness of night, with temperatures crashing to minus 130 degrees Celsius. This 700-degree swing isn't just a number on a thermometer, it's a physical hammer blow. The lunar surface itself expands and contracts with the brutal change, and as the cold of the lunar night grips the ground, the contracting crust cracks and pops, producing thousands of tiny, high-frequency thermal moonquakes every morning. It's the sound of the moon itself groaning as it wakes up from its long, cold night. Finally, there are the most dramatic, but also the most superficial, seismic events, those caused by meteoroid impacts. The Apollo seismometers were perfectly positioned to listen to the moon getting punched. They recorded everything from the gentle pitter-patter of tiny specks of dust to the colossal thud of a 1-ton asteroid slamming into the far side in 1972, an impact so powerful it registered for over 4 hours and would have been felt by an astronaut standing on the surface. These impact quakes provided a valuable bonus. By timing the seismic waves, scientists could accurately gauge the thickness of the lunar regolith, the layer of dusty rubble that covers the moon. The different types of moonquakes produce distinctly different seismic signatures on a data plot. Deep moonquakes show up as a clean, rhythmic, and prolonged wave train, reverberating through the lunar interior for up to an hour. Shallow moonquakes are sharp, violent spikes that decay quickly. Thermal quakes are a chaotic, high-frequency chatter, while impact quakes begin with a single, sharp jolt, followed by a long, slow ringing as the moon vibrates like a giant, dusty bell. This entire seismic catalog is more than just a lunar curiosity. It's the key that unlocked our understanding of the moon's internal structure. By tracking how these different seismic waves traveled and reflected through the lunar interior, scientists were able to create a detailed map of the moon's layers. They confirmed the existence of a crust, a mantle, and even a core, though it is much smaller and denser than Earth's. The data suggests the core is partially molten, a remnant of the moon's fiery birth. This internal blueprint is crucial for understanding not just the moon, but the entire early solar system. The moon is a preserved relic of that era, and its internal structure holds clues to the violent giant impact that is thought to have created it from the debris of a collision between a young Earth and a Mars-sized protoplanet. Every moonquake, from the deep tidal flexing to the shallow tectonic slips, is a piece of that puzzle, a whisper from a world we are only just beginning to truly listen to. From the violent glass-laced storms of distant worlds to the faint, persistent tremors of our own moon, we have explored some of the most active and dynamic phenomena in the cosmos. But what if I told you that all of this, every swirling galaxy and every stellar nursery, is merely the glittering decoration on an invisible, underlying architecture? The grandest structure of all is one we cannot see, a cosmic skeleton that dictates the very arrangement of the universe. This is the cosmic web, a vast network of dark matter filaments that stretches across billions of light years, with galaxies clinging to it like dewdrops on a spider's silk. For centuries, astronomers mapped the heavens and saw galaxies scattered seemingly at random, but as our view widened, a pattern emerged, one of breathtaking scale and complexity. Galaxies are not randomly distributed. They are gathered into immense clusters, strung along winding chains and walls, separated by terrifyingly empty voids so large they could contain thousands of galaxies, yet are almost completely barren. This colossal arrangement is the visible imprint of something far more pervasive and mysterious, dark matter. This invisible substance, which does not emit, absorb, or reflect any light, makes up about 85% of all the matter in the universe. We cannot see it, but we can feel its gravitational influence. In the early universe, slight density fluctuations in the dark matter provided the gravitational seeds for all structure to form. Ordinary matter, the stuff that makes up stars, planets, and us, was simply pulled along for the ride, flowing into the gravitational wells carved out by the dark matter. Over billions of years, this dark matter condensed into a web-like structure, a sponge of sorts on a cosmic scale. The densest knots in this web became the locations of massive galaxy clusters, where thousands of galaxies swarm together. These knots are connected by long, thin filaments of dark matter, and where these filaments intersect, more galaxies form. Between them lie the cosmic voids, regions of profoundly low density that make up most of the volume of the universe. So, how do you map something you cannot see? Astronomers use one of the most elegant tools in their arsenal, gravitational lensing. This phenomenon is a direct prediction of Einstein's theory of general relativity, which tells us that mass warps the fabric of spacetime. A massive object, like a cluster of galaxies embedded in its halo of dark matter, acts like a lens, bending the path of light from more distant galaxies behind it. When we look at these galaxy clusters, we often see the background galaxies stretched and distorted into faint, smeared arcs and multiple images. It's as if we are looking through a giant, lumpy magnifying glass made of dark matter. By meticulously measuring the precise way these distant galaxies are distorted, scientists can work backwards to calculate the total mass of the foreground cluster, including the vast amount of invisible dark matter that holds it together. This allows them to trace the shape and distribution of the dark matter halo, effectively making the invisible visible. The most stunning representations of this hidden architecture come not from telescopes, but from supercomputers. Cosmologists run some of the most complex simulations ever created, like the Illustris TNG or the Millennium simulation. These virtual universes begin with the conditions of the early cosmos and then apply the known laws of physics to model how dark matter, gas, and stars evolve over 13.8 billion years. The results are breathtaking visualizations that show the cosmic web in all its glory. We see the dark matter form a delicate, intricate lattice, a tapestry of filaments and nodes in shimmering hues. The ordinary matter follows this blueprint, with simulated gas flowing along the filaments, cooling, and igniting into galaxies at the intersections. Watching these simulations unfold is like watching the universe grow up, witnessing the birth of its large-scale structure from a nearly smooth, primordial soup into the complex, web-like universe we observe today. These visualizations are not just beautiful, they are a critical test for our theories. When the distribution of galaxies in these simulated universes matches what we see in our real telescopic surveys, it gives us tremendous confidence that our understanding of dark matter and cosmic evolution is on the right track. This hidden framework is the true backbone of the cosmos. Every galaxy we see, including our own Milky Way, resides within a halo of this mysterious substance, and every move we make through the universe is along the invisible threads of this cosmic web. It is the ultimate proof that the most fundamental components of reality are often the ones that remain forever hidden from our direct sight, yet their influence shapes everything we can see. Leaving behind the intricate cosmic web that binds the universe, we venture to the frozen frontier of our solar system, where time itself seems to slow to a crawl. On the dwarf planet Pluto, a single day, the time it takes to complete one full rotation, lasts for an astonishing 6.4 Earth days. This languid spin means that if you were standing on its surface, the sun would take over a week to travel from one horizon to the next, painting the sky with a dawn and dusk that each linger for Earth days at a time. This measurement was pinned down with incredible precision thanks to decades of persistent observation from Earth-based telescopes. which tracked the subtle, rhythmic changes in Pluto's brightness as different, variegated terrains rotated into view. The final, definitive confirmation came from NASA's a New Horizons mission during its historic flyby in 2015. The spacecraft's long-range camera captured a full rotation of the distant world as it approached, creating a mesmerizing time-lapse that showed entire hemispheres slowly turning, their complex patterns of bright and dark regions shifting like the face of a distant, icy clock. This slow dance is a direct consequence of the complex gravitational interplay within the Pluto-Charon system. Charon is so massive relative to Pluto that the two are gravitationally locked, forever facing one another as they orbit a common center of gravity located in the space between them. This tidal locking has acted as a brake over billions of years, synchronizing their spins and contributing to the exceptionally slow rotation we observe today. A single Plutonian day would be an experience of profound patience and dramatic change. Because Pluto's axis is tilted similar to Earth's, it experiences seasons, but each season lasts for decades given its 248 Earth-year orbit. During its long day, the Sun, though over 30 times smaller in the sky than from Earth, would still be the brightest object, casting sharp, long shadows across the alien landscape. The thin atmosphere, primarily nitrogen with traces of methane and carbon monoxide, would create a weak but perceptible blue haze at sunrise and sunset, with the possibility of these gases briefly snowing out as the distant sun's feeble warmth wanes. The surface itself, as revealed by New Horizons, is a stunningly diverse world that would transform dramatically under the shifting light. You might begin your 6-day morning in the vast, heart-shaped nitrogen ice plain known as Sputnik Planitia, a seemingly smooth glacier that is actually convecting slowly, renewing its surface over geological time. As the day progresses, the low-angle sunlight would gradually illuminate the towering, jagged water ice mountains like the Norgay Montes, their peaks reaching several kilometers high. By midday, the sun would highlight the bizarre, bladed terrain of Tartarus Dorsa, where fields of methane ice stand in sharp, skyscraper-sized ridges, possibly formed by erosion over millions of years. And as the long afternoon gives way to an equally protracted evening, you would watch the shadows stretch across the dark, cratered highlands of Cthulhu Macula, a vast region stained with a dark, reddish-thallen material. The New Horizons images provide our only visual reference for this slow-motion day. One stunning sequence shows a fully illuminated hemisphere with Sputnik Planitia glowing brilliantly white, while another view, taken as the spacecraft looked back, captures a dramatic crescent Pluto backlit by the sun, its thin atmosphere forming a beautiful, luminous halo. To witness a full day on Pluto is to understand a world where time is not a fleeting resource but a vast, geological canvas where the sunrises and sunsets are major events, and the landscape holds secrets that reveal themselves only to those who are willing to wait. After exploring the silent tremors of the moon and the invisible architecture of the cosmic web, let's indulge in a fact that appeals to a different sense altogether, the sense of taste. It turns out that the center of our galaxy, a region of unimaginable violence and power, holds a delicious secret. If you could somehow take a sniff and a sip of the vast molecular cloud known as Sagittarius B2 near the galactic core, you would be met with the unmistakable aroma of rum and the sweet, tangy flavor of raspberries. This isn't the premise of a science fiction story. It's a legitimate chemical discovery made by astronomers using some of the world's most sensitive radio telescopes. The key ingredient responsible for this cosmic confection is a molecule called ethyl formate. Here on Earth, this very same compound is the ester that gives raspberries their distinctive taste and contributes to the rich, sweet scent of dark rum. Finding it in the chaotic environment of a stellar nursery is a delightful reminder that the building blocks of complex chemistry, and even the signatures of things we find pleasant are woven throughout the cosmos. The method of this discovery is as fascinating as the find itself. Scientists didn't point a giant telescope and see a raspberry. They used the powerful tools of radio astronomy to listen to the chemical composition of space. Molecules in space don't sit still, they tumble and vibrate, and as they do, they emit light at very specific, characteristic frequencies, much like a musical instrument playing a unique note. Each molecule has its own spectral fingerprint, a set of radio waves it broadcasts into the void. To identify ethyl formate, researchers used the Aram radio telescope in Spain, tuning its receivers to the precise frequencies that this molecule is known to emit. It was like searching for one specific voice in a cosmic choir of chemical transmissions. When they pointed the telescope toward the dense, gas-rich clouds of Sagittarius B2, they found a perfect match. The signal was clear and strong, confirming that vast quantities of this flavorful molecule are present in that interstellar cloud. To visualize this, imagine a stunning, swirling nebula of cosmic dust and gas, glowing with the energy of newborn stars. Now picture a single giant raspberry floating whimsically in the foreground, not as a literal fruit, but as a playful representation of the chemical flavor profile that permeates that region of space. It's a fun and memorable way to anchor this complex scientific finding in something familiar and delightful. The implications of this discovery, however, go far beyond a fun piece of trivia. Ethyl formate is what's known as a complex organic molecule. Its presence in a star-forming region like Sagittarius B2 is a powerful testament to the sophisticated chemistry that occurs naturally in the universe. These molecular clouds are the cradles of solar systems, the raw material from which new stars and planets are born. Finding such molecules there tells us that the ingredients for much more complex chemistry, including the prebiotic molecules that are the precursors to life, are being manufactured in abundance throughout the galaxy and incorporated into new planetary systems from their very inception. It suggests that the universe is not just a sterile void, but a vast chemical laboratory, inherently predisposed to creating the kind of molecular complexity that, under the right conditions, could eventually lead to biology. So, the next time you enjoy the taste of a raspberry, consider the incredible journey of its chemical signature. The same molecular structure that delights your palate here on Earth is also drifting in colossal clouds near the center of the Milky Way, a sweet hint of the interconnectedness of cosmic chemistry and a charming example of how the universe can sometimes surprise us with a familiar flavor in the most unexpected of places. While we have marveled at the preserved footprints left by Apollo astronauts on the lunar surface, a more profound discovery has been made in the shadows openings that lead not to a dusty past, but to a potentially habitable future. Scattered across the moon are deep, vertical pits, often called skylights, which are not mere impact craters, but the collapsed roofs of subterranean tunnels, offering a glimpse into a vast, hidden world beneath the regolith. These features are the surface entrances to what were once rivers of molten rock. Billions of years ago, when the moon was volcanically active, lava flowed across its surface. The outer edges of these lava streams would cool and solidify, forming a solid roof, while the molten rock continued to flow underneath, eventually draining away and leaving behind a long, hollow tunnel known as a lava tube. In some places, a section of the roof has collapsed, creating a near-perfect circular shaft that plummets into the darkness below. The scale of these subterranean caverns is what truly staggers the imagination. Orbiting spacecraft like NASA, a lunar reconnaissance orbiter, have not only spotted these pits, but have also peered directly into them. High-resolution cameras have captured breathtaking images of these skylights, showing sheer walls descending dozens of meters into an abyss. By analyzing the shadows cast deep within these pits, scientists have been able to estimate their incredible dimensions. Some of these subsurface cavities are colossal, with volumes so enormous they could comfortably contain the entire downtown of a major metropolitan city, complete with skyscrapers, all sheltered beneath a solid ceiling of rock. The discovery of these natural lunar caverns has completely transformed our vision for a sustained human presence on the Moon. The surface of the Moon is an incredibly hostile environment. For 14 days at a time, it is baked by unfiltered solar radiation, with temperatures soaring to 120 degrees Celsius. This is followed by an equally long night, where the temperature plummets to a bone-chilling minus 130 degrees Celsius. Furthermore, there is no protective magnetic field to shield against deadly cosmic rays and solar storms, and the surface is constantly bombarded by micrometeorites, tiny specks of dust traveling at supersonic speeds. A habitat built on the surface would require immensely thick walls and complex, energy-intensive systems for both cooling and heating to counteract these brutal extremes. A lava tube, however, offers a pre-built, perfectly engineered solution. The solid rock ceiling, which can be tens of meters thick, provides a formidable natural barrier. It would block more than 99% of harmful solar and cosmic radiation, creating a far safer environment for long-duration stays. It would also offer complete protection from the relentless sandblasting of micrometeorites. Perhaps most importantly, the subsurface environment maintains a remarkably stable temperature, hovering around a comfortable minus 20 degrees Celsius. While still cold, this is a much more manageable and constant baseline compared to the 300-degree temperature swing on the surface, drastically reducing the energy needed to maintain a habitable climate inside a future base. The potential for these lunar caves extends far beyond simple shelter. They could serve as the foundational infrastructure for an entire lunar colony. Within these vast, shielded volumes, we could construct pressurized modules for living and working, using the cavern walls as a natural foundation. The constant, benign temperature would be ideal for storing sensitive equipment and supplies. There is even the tantalizing possibility that the perpetual darkness in the deepest recesses of these tubes has preserved water ice, trapped there for billions of years, which could be mined for life support and rocket fuel. The imagery that brings this concept to life is both eerie and inspiring. High-resolution photos from lunar orbiters show these pits as stark, black circles set against the gray, sun-baked landscape. In some images, you can see where a section of the crater wall has slumped inward, creating a gentle ramp, a potential natural entrance for future explorers and their rovers. Other views, taken when the sun is at a low angle, illuminate the upper portions of the cavern walls, revealing layered bedrock and hinting at the immense, cathedral-like space that lies beyond. These are not just holes in the ground, they are gateways, offering a ready-made sanctuary that could protect humanity's first outpost on another world, turning a lethal environment into a place we could one day call home. Now, let's dive into one of the most profound and heated debates in modern cosmology, a puzzle so deep it challenges our most fundamental understanding of the cosmos. Astronomers have two primary methods for measuring a single, crucial number: the Hubble constant, which tells us the current expansion rate of the universe. The first method looks back to the universe's infancy, using the afterglow of the Big Bang, the cosmic microwave background, as a fossilized snapshot. The European Space Agency's Planck satellite mapped this relic radiation with exquisite precision, and by applying our well-tested model of cosmic evolution, scientists can calculate what the expansion rate should be today. This method gives us a value of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, or 3.26 million light-years of distance, a galaxy is moving away from us 67.4 kilometers per second faster. The second method, pioneered by the Hubble Space Telescope and other observatories, measures the rate directly in our local, modern universe. It uses a cosmic distance ladder, carefully calibrating the distances to nearby stars and then to more distant galaxies that contain a special kind of pulsating star called a Cepheid variable, and finally to galaxies hosting a specific type of supernova explosion. This painstaking step-by-step approach yields a different answer, approximately 73 kilometers per second per megaparsec. Now, a difference of 5 or 6 might not sound like much, but the uncertainty in both measurements has been squeezed down so tightly that the chance this is a simple error is less than 1 in a million. We are not just dealing with a minor statistical fluke, we are staring at a fundamental discrepancy. This is the Hubble tension, and it suggests that something is missing from our cosmic recipe book. To visualize this conflict, imagine a graph showing the expansion rate of the universe over cosmic time. The Planck data point sits confidently at the beginning of the timeline, and our standard model of cosmology draws a smooth, predicted curve from that early point to the present day. But then, the Hubble data point, measured in the local universe, sits visibly and stubbornly above that predicted curve. It's as if you carefully calculated the path of a rocket based on its launch, only to find it is now miles off course. This isn't just two lines failing to meet, it's a direct challenge to the lambda cold dark matter model, the foundational framework that has successfully described our universe for decades. So, what could be causing this rift? Cosmologists are exploring several thrilling and some truly radical possibilities. One compelling idea is that dark energy, the mysterious force driving the accelerated expansion of the universe, is not constant as we've assumed. Perhaps it has been evolving over time, growing stronger in the recent cosmic past, which would give the local expansion rate an extra kick that our models didn't account for. Another fascinating proposal involves early dark energy, a new form of energy that may have existed for a brief period in the universe's first few 100,000 years, subtly altering the conditions at the dawn of time and throwing off the Planck prediction for the present day. Other theories venture into even more exotic territory, suggesting the existence of new types of neutrinos, often called sterile neutrinos, or a previously unknown interaction between dark matter and normal matter. Some have even entertained the possibility that our universe is not perfectly uniform on the largest scales, and that we live in a local underdensity, a cosmic void, which could make our local measurements of the expansion rate appear artificially high. Each of these potential solutions would require a significant rewrite of our physics textbooks. The implications are staggering. If the discrepancy is real and points to new physics, it would be one of the most significant discoveries of the century, offering a direct window into the nature of dark energy, dark matter, and the fundamental forces that have shaped cosmic history. The scientific community is now racing to resolve the tension with new, independent methods, such as using gravitational waves from colliding neutron stars as standard sirens to measure cosmic distances without the need for a traditional distance ladder. The resolution of this conflict, whether it confirms our standard model or forces us to invent a new one, will undoubtedly redefine our place in the cosmos and reveal a universe that is, once again, far more mysterious and dynamic than we ever imagined. From the silent, preserved history on the moon to the faint, rhythmic tremors that shake it, we have encountered cosmic phenomena that challenge our senses. But now prepare to witness a concept that seems to defy the very laws of physics, a black hole that sings. We've all been taught that in the vacuum of space, no sound can travel, yet at the heart of the Perseus galaxy cluster, 250 million light-years from Earth, a supermassive black hole is producing the deepest note ever detected in the universe. This isn't a metaphor for some abstract electromagnetic vibration. It's actual sound, real pressure waves rippling through the incredibly hot, thin plasma that fills the space between the galaxies in that cluster. The discovery was made by astronomers using NASA Chandra X-ray Observatory, which is uniquely equipped to see the multimillion-degree gas that pervades such clusters. When they studied the X-ray data from Perseus, they didn't just see a static cloud of gas, they saw a stunning, ripple-like pattern concentric circles of slightly denser and hotter gas expanding outward from the central black hole like ripples on a pond. These ripples are sound waves, colossal waves of pressure generated by cyclical explosions from the black hole itself. The process is a cosmic feedback loop. As matter spirals into the supermassive black hole, it doesn't all cross the event horizon. Some of it is funneled and accelerated into powerful jets that shoot out from the poles, injecting tremendous energy into the surrounding gas. This energy injection happens in pulses, and each pulse acts like a mighty drumbeat, sending a spherical sound wave propagating through the cluster's plasma at hundreds of kilometers per second. The scale of this acoustic phenomenon is almost impossible to comprehend. The wavelength of this sound, the distance between the crest of one wave and the next, is a staggering 35,000 light years. That's over 1/3 the diameter of our entire Milky Way galaxy. For a sound wave to have such an immense wavelength, its frequency must be incredibly, almost unimaginably low. The note this black hole is singing is a B-flat, but it is 57 octaves below middle C on a piano. To put that in perspective, a piano has only 7.5 octaves. This note is so deep that its frequency is a 10 million billion times lower than the lowest sound the human ear can detect. It is a vibration on a truly cosmic scale, a hum so profound it makes the planet itself seem like a tiny, high-pitched chime. Of course, we could never stand near this black hole and hear its song with our own ears. The frequency is far too low, and the environment would instantly vaporize us. But through the powerful technique of data sonification, scientists have scaled up this cosmic vibration, bringing it into a range we can experience. They took the actual pressure wave data from the Chandra observations and multiplied its frequency by an astonishing factor of 290 quadrillion. What emerges from the speakers is not a melodious tune, but something far more primal and haunting. It's a deep, resonant, groaning hum, a sound that evokes a sense of immense age, power, and loneliness. It is the voice of a gravitational titan, a low-frequency drone that has been echoing through that intergalactic void for hundreds of millions of years. Let's listen to it now. This sound is more than just a spooky scientific curiosity. It has profound implications for the evolution of galaxies. For decades, astronomers wondered why the central regions of galaxy clusters like Perseus are not churning out new stars at a furious rate. The gas there is dense and should be cooling and collapsing to form stars, yet it isn't. The singing black hole provides the answer. This deep, resonant hum, these powerful sound waves, are a primary mechanism for heating the surrounding gas. As the waves travel outward, they dissipate their energy, much like the sound from a speaker eventually turns into warmth. This sonic heating acts as a cosmic thermostat, preventing the gas from cooling down enough to fragment into stars. The black hole, through its own violent consumption of matter, is singing a lullaby that suppresses the birth of new suns, regulating the growth of its entire galactic home. This creates a beautiful and self-regulating balance between the monster at the center and the galaxy it inhabits. It is a stark and awe-inspiring reminder that the universe is not a silent film, but a full sensory experience, filled with vibrations and rhythms that play on scales both infinitesimally small and galactically large, connecting the most destructive forces in nature with the creation of cosmic structure itself. But while we have mapped the orbits of planets and even predicted the existence of a distant Planet 9, the true outer boundary of our solar system is not marked by a single world, but by a ghostly, spherical shell of primordial ice. This is the Oort cloud, a theoretical reservoir of frozen relics that forms the ultimate frontier of the Sun's gravitational influence, a place so distant it redefines our sense of home. Imagine taking every rocky planet, every gas giant, and every tiny ice ball in the Kuiper belt, and placing them all inside a sphere centered on the Sun. Now expand that sphere until its inner edge is about 2,000 astronomical units away, and its outer boundary stretches to a mind-numbing 100,000 astronomical units, nearly halfway to the nearest star. That is the scale of the Oort cloud, a vast, tenuous swarm of perhaps trillions of icy objects held in the Sun's faintest gravitational embrace. To truly grasp this distance, picture a diagram of our solar system. The Sun is a tiny, brilliant pinprick at the center. The orbits of the planets are crowded so close to it they appear as a single, tangled ring. Pluto's orbit, which seems so vast to us, is just a slightly wider loop. But then you must travel through an immense, seemingly empty gulf to reach the inner fringe of the Oort cloud, a region so far that light itself takes weeks to travel from the Sun to its innermost objects. The entire cloud forms a colossal spherical shell, encasing our entire planetary system like a cosmic eggshell, with the Sun and all its planets as a mere speck at its center. This isn't a structure we can photograph. Its existence is inferred from the behavior of the most mysterious visitors to our inner solar system, the long-period comets. These are the spectacular, sun-grazing wanderers that appear without warning, often with orbits so elongated they take thousands or even millions of years to complete a single journey around the Sun. Astronomers realized that these comets couldn't originate from the flat disk of the Kuiper belt, as their orbits are not confined to the plane of the planets. They come from all directions. The only explanation is a vast, spherical reservoir, the Oort cloud, which acts as a deep freeze storage unit for these icy bodies. Occasionally, the gentle gravitational nudge from a passing star or the tidal pull of the Milky Way galaxy itself will dislodge one of these frozen planetesimals, sending it on a long fall inward toward the warmth of the Sun. The journey from the Oort cloud to the inner solar system is an epic voyage. A comet kicked loose from the cloud's outer reaches might travel for millions of years in the darkness before its ices finally begin to vaporize in the solar heat, blossoming into the magnificent tail we see from Earth. This makes every long-period comet a messenger from the solar system's very earliest days. The objects in the Oort cloud are the pristine, unused building blocks from the solar system's formation over 4.6 billion years ago. They were likely formed much closer to the Sun, in the region of the giant planets, but were violently scattered outward by gravitational encounters with Jupiter and Saturn when the solar system was young. This scattering process flung them into the abyss, where they have remained, virtually unchanged, in a state of cosmic suspended animation ever since. The sheer number of objects hypothesized to be out there is staggering. Estimates suggest the Oort cloud may contain several trillion icy bodies, each a potential comet nucleus. Yet, despite this unimaginable population, the cloud is mostly empty space. The average distance between these objects is likely tens of millions of kilometers. If you were to fly a spacecraft through the Oort cloud, you would almost certainly never see one, even as you passed through the most densely populated regions. This makes the Oort cloud less of a cloud and more of a fantastically vast and diffuse halo, a gravitational concept made manifest. It represents the final transition from our solar system to the true interstellar medium, the point where the sun's pull finally yields to the gentle tide of the galaxy. Contemplating its existence forces us to expand our definition of where the solar system ends and the rest of the galaxy begins, reminding us that our home is not just a family of planets, but an immense sphere of influence, with its farthest reaches touching the stars themselves. And so we arrive at our final, and perhaps most fundamentally mind-bending, fact of all, one that challenges our most basic experience of reality. On Earth, time feels like an absolute river, flowing at the same steady rate for everyone and everything, everywhere. But this is an illusion. The universe, as described by Einstein's theory of relativity, operates under a far more bizarre and beautiful set of rules. Time itself is malleable. It stretches and compresses based on two things, gravity and speed. This phenomenon is known as time dilation, and its effects, while tiny in our daily lives, are very real and must be accounted for, even here on our own planet. Let's break down these two incredible ways that time can slow down. The first is due to gravity, described by Einstein's general theory of relativity. Think of the fabric of spacetime as a flexible, stretched rubber sheet. A massive object like the Earth creates a deep dimple in this sheet. The closer you are to that mass, the deeper you are in the gravitational well, and the more spacetime is warped. One of the consequences of this warping is that time itself runs slower. Imagine two identical clocks, one placed on the Earth's surface and the other launched high up into space, far from Earth's gravity. If you could compare them after a while, you would find that the clock in the weaker gravity of space has ticked faster than the clock on the ground. The clock on Earth, deeper in the gravity well, has literally experienced less time. The second way time slows down is due to speed, as per Einstein's special theory of relativity. The faster you move through space, the slower you move through time. It's as if the universe has a fixed speed budget for your existence, and any speed you spend on moving through space is taken away from your rate of moving through time. If you were to hop on a super-fast spaceship and travel at 80% the speed of light for what feels like a year to you, you would return to Earth to find that many more years had passed for everyone you left behind. This isn't a mechanical error in your clock, it is the actual relative passage of time. Now, you might think these effects are so small they're only theoretical, but we rely on them every single day. The Global Positioning System, or GPS, is a perfect, practical example. The network of GPS satellites orbiting Earth are both high above our planet's gravity and moving at tremendous speeds of about 14,000 kilometers per hour. These two relativistic effects actually work against each other. Because they are high up, their clocks run faster due to the weaker gravity, but because they are moving so fast, their clocks run slower due to their velocity. It turns out the gravitational effect is stronger. If the engineers who designed the GPS system did not account for this, the clocks on the satellites would gain about 38 microseconds per day. A microsecond is a millionth of a second, but that tiny error would compound rapidly, since the system uses precise timing to calculate your position, and light travels almost 300,000 kilometers in a single second. An uncorrected error of 38 microseconds would throw off your location by about 10 kilometers per day. The entire system would become useless in a matter of hours, so the software on every single GPS satellite is deliberately programmed to run its internal clocks slightly slower before launch, specifically to counteract Einstein's predictions and keep you from getting lost on your way to the grocery store. The same principle applies to our astronauts on the International Space Station. They are living in an environment where time is passing very slightly faster for them than for us on the surface. Over a typical 6-month mission, The combined effects of their speed and their position in Earth's gravity well mean that an astronaut actually ages about 0.005 seconds less than the rest of us. They return to Earth having experienced a tiny bit less time. They are, in a very real sense, a fractional second younger than they would have been if they had never left the ground. To make this abstract concept more intuitive, consider one of the most famous thought experiments in all of physics, the twin paradox. Imagine a pair of identical twins. One stays on Earth, while the other boards a spaceship and travels to a distant star at a significant fraction of the speed of light. From the perspective of the twin on Earth, the traveling twin's clock appears to be ticking slowly. When the traveling twin finally returns home, they step out of the spacecraft not as an identical twin, but as a younger sibling. The one who journeyed among the stars has aged less. This has been confirmed not just with satellites, but with incredibly precise atomic clocks here on Earth. Scientists have placed two identical atomic clocks in sync, then flown one around the world on a jet aircraft. Upon its return, the clock that traveled is ever so slightly behind the one that stayed put, exactly as relativity predicts. Animations can bring this bizarre reality to life. Picture a simple grid representing the flow of time. As an object moves into a strong gravitational field, the grid lines bend and stretch apart, showing time expanding and slowing down. Or visualize a spaceship accelerating to near light speed, with a clock inside it visibly ticking slower and slower compared to a stationary clock next to it. These visual metaphors help us grasp a concept that our everyday intuition rebels against. This is the profound truth of our universe. There is no single, universal now. Your past, present, and future are relative, intimately tied to your motion and your position in the gravitational landscape of the cosmos. The steady, reliable tick of a clock is not a constant drumbeat for all of creation, but a personal rhythm, a unique melody played out for every single particle, planet, and person, woven into the very fabric of a dynamic and relative spacetime. And so, our journey through the cosmos draws to a close, a voyage that has taken us from the silent, eternal footprints on our moon to the singing heart of a distant black hole, from worlds of diamond and glass rain to the invisible, web-like architecture that binds the entire universe. We have witnessed time stretch and compress, seen storms that dwarf our planet and persist for centuries, and discovered that the fundamental ingredients for life are scattered like cosmic seeds throughout the galaxy. These 30 facts are not just a collection of trivia, they are a testament to a universe that is infinitely more creative, more bizarre, and more magnificent than the simplified diagrams of any textbook could ever hope to convey. They reveal a cosmos where the laws of physics are not just equations on a page, but living, breathing forces that sculpt realities beyond our wildest dreams, where the line between science and science fiction constantly blurs, inviting us to question everything we think we know. This journey underscores a profound truth. Our planet is a fragile, beautiful oasis in a vast and dynamic ocean of existence, but it is not an isolated one. We are intimately connected to this grand cosmic dance, our very bodies and the atoms within us forged in the hearts of long-dead stars, our sense of time and space relative to our journey through the universe. The familiar night sky is not a static painting, it is a living, breathing entity filled with the whispers of comets, the groans of moons, the silent, patient growth of diamond worlds, and the hum of gravitational tides. Each fact we've explored is a key, unlocking a door to a deeper understanding, replacing cold, distant knowledge with a sense of awe and personal connection to the cosmos. Now, this is where the adventure truly begins for you. The next time you find yourself beneath a clear, starry night, I encourage you to step outside and simply look up. Let your gaze wander, See if you can spot the steady glow of Jupiter or the ringed splendor of Saturn. Trace the hazy band of the Milky Way, our home galaxy, and remember that near its center, a cloud carries the flavor of raspberries. Consider our own moon not as a dead rock, but as a world with a heartbeat, its surface holding our most enduring mark and its subsurface hiding caves that could one day shelter human explorers. Let that sense of wonder wash over you. The universe is not a remote, abstract concept. It is your inheritance, a story still being written, and you are a part of it. We would love to continue this conversation with you. In the comments below, tell us which of these 30 facts reshaped your perspective the most. Was it the cosmic latte that paints the universe in a gentle beige, or the hexagonal storm at Saturn's pole? Did the thought of a room temperature star or the eternal lunar footprints capture your imagination? Sharing your thoughts helps build a community of curious minds, all looking up together in wonder, and if this journey has ignited a spark of curiosity, if you're eager to keep exploring the mysteries of black holes, the search for alien life, or the secrets of dark matter, then make sure to subscribe to the channel. We're just getting started, and there are countless more cosmic adventures waiting, each one designed to challenge your assumptions and fill you with the profound wonder of our incredible universe. Thank you for joining us on this expedition. Keep looking up, keep questioning,